Well, no, I thought we were farther ahead. Yeah, so we're on the next slide, yes? Because I think we finished this ABCD. And I need to go back and change the note sheets and flip C and D so it matches, so we're not crossing back over. All right, guys, we're going to go on and get started with this here. So we did work through these here Friday because we got through all of these here before we stopped and the bell rang. But we saw how we can work these here, because if I get the base and what's inside the logarithm to be the same, then it simplifies to 1. Or we rewrote these in exponential form and went from there. So there's different ways we can go about doing this. Some of the ways are kind of limited to us because we haven't got to those properties yet and how it works, but we'll get to them eventually. Now, when we look at these here, these next set of 4, log base 4 of 256. Everything's all contained, yes? So if you don't have a graphing calculator, I might go on and grab one, because it might be helpful for this here. Now, as we've stated already, we can't just use the log button, because if we're doing log, because both calculators have that log button, the base has to be 10. Because if the base is 10, we can use the log button, everything works fine. But if we look at the problem, the first one we're looking at here, A is log based 4. So we can't just plug it in. We wouldn't do second math, but if we hit math, so it's right under alpha. And if we scroll up, we see one of the options is log base. Now we could scroll up or down, it doesn't matter which direction. For this here, it's a little bit quicker to go up than it is to go down. And hit enter. If you notice for this here, it actually gives us the ability to type in a base. Here, our base is 4, and our number is 256. And the answer is 4. Huh? So x equals 4? We could say that the answer is 4. Yep. Because when the number... Yeah, because I think it's good to see the relationship between it and how it works, because here we're really trying to say in exponential form, 4 to what power is 256? Well, the exponent that we need for this is indeed 4. Our next one, log base 8 of 0.125. So we can go math, log base 8 of 0.125, and it is -1. Math, log base, so 1/3. There's 2 ways we can do this. If we want to type it in as a fraction, alpha y equals enter. Alpha y equals enter. 1/3 log base 1/3 of 27 is alpha y equals enter. So let's try it. So question was, can we put it in as a decimal? So 0.33333. So this here, because 1/3 is 0.3 repeated. So it would work, but we'd have to put a lot of 3's. Now, fractions are just another way of doing what operation? Dividing. It's just division, yes? So, guys, focus back up here. Because again, fractions are just division. We're just dividing the numerator by the denominator, the top by the bottom. So we could say 1 divided by 3, and then do 27, and we get the same thing. Yeah. So sometimes it's easier to just write it in as division than it is to do alpha y equals enter and pull that fraction up. One divided by 3. Top of the fraction divided by the bottom. And the last one, log base 64 of 8. So we get 0.5. Now if we do math, enter, because that first thing is fractional, we can turn it from a decimal to a fraction. It depends on the decimal. Because here 0.5 is nice. 0.5 is a nice decimal, 1/2, 0.5. Both of those are fine. Now, I'm going to change this just a little bit. Because if we said log base 64 of 4, this is not as nice of a decimal. It is 1/3. Math. It's 1/3. Because our these repeated decimal numbers, it's easier or nicer to write them as a fraction. 0.5, 1.5, those are nice either way. If we're having to approximate or have to draw our rounding bar, might as well put them as a fraction. Does that make sense?
Yep, you bet.
Questions on this here? So at the very top where we graphed. Yep. So when I say y equals, that's the button I'm talking about. Because I'm just really referencing the fact that it has y and then equals. It might have been rubbed off over the years. So this works nice, yes? Because if we're evaluating this here, these are nice. Now, there are going to be times when we start solving. Where we're not going to be able to type this in. Because log base 4 of x equals 4, we can't type it in because one of the parts of the logarithm is a variable, not a number. But when we're given the base and what's inside the log, we can type that in, let the calculator do it for us. Because everything's a number. Here, well, we would have 4 to the 4th is equal to, so I converted it from logarithmic to exponential, and it would tell us that it's 256. So sometimes just switching it over to logarithmic will make the difference. Now there is another type of logarithm, and it's a natural logarithm. Natural logarithms. Yes. The natural log of x equals y, if and only if e to the y is equal to x. Natural logs will not have a base other than e. So the base for any natural log is understood to be e, and it never changes. For any of our other LOGs, our logarithms, we could have 10, we could have any base. But natural logs is always e. And with our logarithms, if the base is 10, we don't have to write the 10. I wanted us to write it on Friday, so we got used to seeing it and knowing it's there. And once we get used to that, we don't have to write log base 10 of x. We can just write this as log of x because it's understood. Natural log is the same thing. We don't have to write the e, but we need to know that it is there. So I'm going to write this back up again. So we said ln of x is equal to y if and only if e to the y is equal to x. Or really we can say x is equal to e to the y. I'm going to write it that way. Okay. Now we did this on Friday, and I think it'll be helpful for this here. Our base for this here is understood to be E. In our general equation, the x spot was, so this here is 6. Our y spot is being taken the place by x. And it's a little weird because x is showing up twice in the general form and in actually the equation. But if we rewrite this out, x 6 is equal to e to the x. Yeah, well, y is x because it's on the, so we're just lining them back up. Because when we looked at these the other day with logarithms, log base b of x equals y, b to the y is equal to x, same thing. Questions on this here? So looking at the next one, ln of 5a equals b. Well, what's our base? What's understood to be? E, yes? Ln of x equals y, if and only if x is equal to e to the y. So what number is going to become by itself? Or what spot? Well, it's what's inside the logarithm, yes? So that would be 5a equals e to the b. It's the same, so what we did with logarithms, if you think about how we did this with log, it is the exact same thing. It's just that the base is understood to be e. We don't have a number other than e for the base. Questions on this here? Instead of the base being a number, it's just e. So we have here the natural log of 42 is equal to b. So if we want to rewrite this, this would become what? E to the b is equal to 42. Questions on this here? How about the next one? The natural log of z equals 6. Z is equal to e to the 6, or e to the 6 is equal to z. Either way works. And it seems odd that we're using variables in these here. And that's because if we look at this last one here, e to the 6th. E to the 6 is a non-repeating, non-terminating decimal. It's going to be an irrational number. E is 2.71. It is in the same category as pi. 2.71828. And it's a non-repeating, non-terminating decimal. It seems like it does repeat here, but if we keep going on, it doesn't end. So it keeps going. It never ends, and it doesn't repeat. It does look like it repeats there, but I think the next number after that breaks that pattern. It is exactly like pi. Yep. Well, 3 is bigger than that. It just means that decimal, as we calculate it out, does not end. We keep getting new numbers as we expand out past it. Questions on these two here? Ln of 4 to the y is equal to d. This would be what? 4y is equal to e to the d. Even though the number inside has an exponent, it doesn't change what we're doing. 3 to the a is equal to e to the e. Yeah. It is weird looking, but that's how this goes. You're good. Questions on this here? Yes, ln of y equals 2x. Because if we're given e to the y equals x, this is true if and only if ln of x is equal to y. It's just the opposite. And if you notice, this is the exact same thing we did with logarithms Friday, but instead of rewriting the base, it's understood to be e. And since our base on this set is all e, we don't have to rewrite it back in. So our e to the 57 equals z would be ln of z is equal to 57. Question. Yeah, because this is our base. Let's get a different color. Because our base here is understood to be e. Because in this setup here, our 57 would be the y. Z would be the x, and our base is e. Questions on this here? Yeah. Because we can write it with quotation since it's an individual term. We can write it without. It doesn't matter. The only time it really does matter is if we had, say, e plus 2, we had two terms being added together that had to be contained inside the logarithm. Then we would need the parentheses. So e to the 9y equals? Almost. So ln of what? ln of 6 equals 9y. Ln of 6 equals 9y. All right, guys, let's focus in here. Yeah, ln, because it's standing for our natural logarithm. I have no idea why they flipped it and it's not NL for natural log. Yeah. E to the b equals 4 would be rewritten to? Yep, ln of 4 equals b. Questions? Focus in here, focus in here. Questions on any of these here from switching from natural logarithmic form to exponential or exponential to natural logs? It will be out of the work, it's quote unquote worksheet. It's out of the book. These are the last 4 we're going to do. So we do have 2 in the problem and then 4 more. This first one. Now, all right, I'm going to add this thing here. Log of x. This is understood to be kind of our common log because the base is 10. We call it a common log. Our common natural log is just ln of x because ln of x is just our common log because the base is always e. Now, if we look at this first one here, log of 8 is a common log because the base is understood to be 10. But since the base is not given, I could say log of 8. Type it into the calculator, neither one. Yep. And we get 0.903089. We're going to go 4 decimal places, so 9031. So question on how we found log of 8. ln of, was it 3? 0.3. 2040, yep. Negative 1.2040. Yep. And it says 3 decimal places. We'll go 4. Either one works. Yep, ln is right. It's normally put right next to the log button. Yep. Yeah, they always put those two right next to each other. Yep, so that's if it's our common log, so the base is not written for our log, we can just use the button. Now, something we can expect with this here, because our common logs, as we said, the base is understood to be 10, yes? So log base 10 of x equals y. If I wrote this in exponential form, we're saying that 10 to the y is equal to x, yes? Well, the first one we solved, or we were looking for, our value of x was 8, yes? So we're really saying 10 to what power is 8? Well, 10 to the first is what? 10, yes? So if I'm looking for 8, I'm expecting whatever that exponent to be less than 1. Because if it is 1, it should be equal to 10. That also means if this number is between 10 and 100, because 10 squared is 100, we should expect this number to be between. So log of 81 should be bigger than 1, but smaller than 2. Which is the case. Because 10 to the first is 10. 10 squared is. This is just interpreting the answer. Because we know whatever that number is that's put into the log for our natural logs, well, since it's between 10 and 100, the answer should be between 1 and 2. But that's neither here nor there. Log of 98. So when y'all checked, guys, focus up here, guys. Log of 98 is 1.9912. Did we get that? Log of 9.8. 0.9912, yep. And that'd be correct. ln of 7.84. And the last one, the natural log of 79 over 2. 763. That's it. That's it.